You did everything right. The answer is sitting in your corpus, the embedding model is solid, and cosine similarity still hands the model the wrong chunk. That's not bad luck. It's one of 4 distinct, predictable failures inside Retrieval, the kind that never show up in a 10-document demo. Each has a specific cause and a specific fix, and none of them involve blaming the model. Here's a scenario that trips up a lot of teams. You ask your RAG system a specific factual question, something like, what's the maximum retry timeout in the payments config? The answer comes back fluent, well-formatted, and completely wrong. You go check the source documents, and the correct fact is right there, sitting in the index, chunk 17 of the config reference. So the natural conclusion is that the model hallucinated. But if you actually log what got passed into the prompt, you'll usually find something else entirely. The correct chunk was never retrieved. It wasn't in the top 3, it wasn't in the top 10. Sometimes it isn't even in the top 50. The model was handed 5 chunks of plausible sounding but wrong context. And it did exactly what language models do with context. It answered faithfully from what it was given. That's the part worth sitting with. The generation step worked perfectly. Given those 5 chunks, that answer was a reasonable synthesis. The failure happened earlier, upstream, in the part of the pipeline that decides which text even gets a chance to be read. Blaming the model here is like blaming a translator for mistranslating a page nobody handed them. The retrieval stage silently failed, and generation just executed on bad inputs without complaint, because it has no way of knowing what it wasn't shown. So the real question isn't why did the model get it wrong, it's why did the retriever rank the wrong chunk higher than the right one? That question has a specific mechanical answer, and it starts with how the document got cut into pieces in the first place. Before picking apart why retrieval fails, it's worth being precise about what the standard pipeline actually does, because it's genuinely reasonable engineering. You take your documents and split them into chunks, maybe 200 to 500 tokens each. Every chunk gets run through an embedding model, which turns it into a vector, a list of a few hundred to a couple thousand floating point numbers that's supposed to capture what that chunk means. All those vectors get loaded into an index, something like FAISS or pgvector or a hosted vector database. Then, at query time, you take the user's question and embed it with that same model, so it lands in the same vector space. You compute cosine similarity between the query vector and every chunk vector, and pull back the top k, usually somewhere between 3 and 10. Those chunks get concatenated and pasted into the prompt as context, and the model generates its answer from that. And this pipeline does work. If someone asks a self-contained question, and the answer lives in one short paragraph that uses similar vocabulary to the question, the right chunk usually has the highest cosine similarity. It lands in the top few results, and the model answers correctly. That's exactly why teams ship it. It passes every demo, every quick sanity check, every single fact test someone runs during the pilot. The problems don't show up on question 1. They show up later, and they show up specifically at the seams, how the document got cut, what the embedding actually encoded, how the query was phrased, and what got left out of the vector entirely. 4 things go wrong at the seams, and they go wrong quietly, which is what makes them so hard to catch in a demo. The first is chunking, and it's more damaging than people expect. Say the config document has a line like max retry timeout, followed a few sentences later by the actual number, 30 seconds, inside a table or a footnote. A fixed size splitter cutting every 300 tokens doesn't know that number belongs to that entity. It cuts wherever the token count runs out. So the entity name ends up in chunk 17, and the value describing it ends up in chunk 18. Once those 2 pieces are embedded separately, they're no longer one fact. They're 2 vectors sitting in 2 different neighborhoods of the embedding space, and neither one alone answers the question. The second failure is about what embeddings actually encode. A general-purpose embedding model is trained to place similar topics near each other, not to place answers near questions. Retrieval-tuned models like Text Embedding 3, E5, and BGE are trained on query passage pairs specifically to narrow that gap. And they do narrow it, but they are still ranking by similarity in a shared space rather than judging whether a chunk answers the question. So a chunk that talks broadly around retries, backoff strategies, and timeout configuration in general terms can score a higher cosine similarity than the one specific chunk that just flatly states the number. The retriever isn't wrong about similarity. It's answering a different question than the one you asked. It's finding what's topically adjacent, not what's factually responsive, and those are not the same ranking. Third is query representation, and this one bites on compound questions. Ask something like, what's the retry timeout, and which team owns that service? And you embed that whole sentence into a single vector. That vector is a blend, and blends get pulled toward whichever clause has the stronger, more distinctive signal in the training distribution. Ownership questions tend to have sharper, more common phrasing than config values do, so the vector drifts toward the ownership half, retrieves chunks about team structure, and the retry timeout clause gets starved of representation entirely. One vector cannot cleanly point at two separate targets at once. And fourth, there's no concept of time or authority baked into any of this. If your corpus has a deprecated document and its replacement, and they're both describing the same setting in nearly identical language, their embeddings will be almost indistinguishable. Cosine similarity doesn't know which one was written last month and which one was superseded 8 months ago. It'll rank them side by side, sometimes with the outdated one slightly ahead, and hand your generation step a confidently wrong, expired fact, with no signal anywhere in the vector that it should have been discounted. None of these four are exotic edge cases. They're structural properties of splitting text by length, embedding for topic, encoding one query as one vector, and storing meaning without storing time or trust. Each one produces the exact same symptom from the outside, a wrong answer with no error thrown, which is exactly why the fix has to happen at the mechanism level, not by adjusting the prompt after the fact. Each of those four failures has a specific fix, and the fixes map directly onto the mechanism that broke, not onto the model's behavior. Start with chunking. The problem was that a fixed size splitter cuts by token count with no awareness that an entity and its value might sit on opposite sides of that cut. The fix is overlapping windows, instead of splitting the document into clean, adjacent 300 token blocks. You slide the window forward with, say, 100 tokens of overlap between consecutive chunks. That means the sentence naming max retry timeout and the sentence a few lines later, giving the value 30 seconds now, have a real chance of appearing together in at least one chunk, even if a boundary falls somewhere in between. You're not preventing every bad cut. You're making sure the same fact gets a second chance to be embedded whole in a neighboring chunk, instead of getting permanently split by wherever the token counter happened to land. Next, the embedding semantics problem, where a broad, topically similar chunk outscores the one chunk that actually answers the question. This one doesn't get fixed at the embedding stage. It gets fixed after retrieval, with a cross-encoder re-ranker. A standard embedding model scores the query and each chunk independently, then compares vectors after the fact, which is what causes the topic versus answer confusion in the first place. A cross-encoder does something structurally different. It takes the query and one candidate chunk together, concatenated, and runs them through the model jointly, producing a single relevant score for that specific pair. You do this for your top 20 or 50 candidates from the first pass, then resort by that score. It's slower, so you only run it on a short list, not the whole corpus, but it directly evaluates whether this chunk answers this query, instead of whether this chunk lives near this query in vector space. That's the mechanism that catches the flat, specific sentence, the first pass buried under a paragraph of general context. Then there's the exact identifier problem, which shows up constantly with error codes, version numbers, config keys, anything that's more of a string than a concept. Embeddings are built to blur similar things together, which is exactly backwards for a token like ERR4471 or V2.3.9, where you don't want it blurred with anything, you want it matched exactly or not at all. The fix is hybrid search. You run a keyword method like BM25 alongside the vector search in parallel, and combine both rankings, often with a weighted merge or reciprocal rank fusion. BM25 doesn't care about meaning, it cares about literal term overlap, so an exact error code or version string that vector search smears across a topic cluster gets pulled straight to the top by the keyword side. Vector search still catches the paraphrase, the case where someone describes the config without naming it exactly. Keyword search catches the string match, vector search misses. Vector search catches the meaning match, keyword search misses. Running them together closes both gaps instead of picking one and eating the other's blind spot. Last is the compound query problem, where one question actually contains two distinct information needs and one embedding vector can't point cleanly at both. The fix here happens before retrieval even runs. Query rewriting takes the incoming question and, using a small model call, decomposes it into its separate sub-questions. What's the retry timeout, and which team owns that service, become two independent queries instead of one blended one. Each subquery gets embedded and retrieved on its own, against the full index, so neither one has to compete with the other for representation inside a single vector. The results get merged afterward, once each half of the original question has already been answered on its own terms. None of these four fixes touch the generation model at all. Query rewriting does call a model, but a small utility one, and it runs before retrieval rather than after it. They change what gets cut, what gets scored, what gets searched, and what gets asked, before generation ever sees a token of context. And that raises the obvious next question, which is what happens when the fact itself isn't wrong or missing, it's just outdated, sitting right next to the version that superseded it. Each of these 4 fixes solves a real mechanism, but every one of them costs something specific, and it's worth naming the cost plainly instead of pretending these are free upgrades. Cross-encoder re-ranking means running a full model inference pass over every candidate in your shortlist, not just embedding lookup. So if you re-rank 50 candidates per query, that's 50 extra forward passes on top of the retrieval you already did. Latency multiplies, sometimes by a factor of 3 or 4, and if your traffic is high, so does compute cost. That's fine when correctness matters more than speed, and much worse when a user is waiting on a chat response in real time. Hybrid search has its own tax. You're no longer running one clean vector store. You're maintaining a keyword index like BM25 and a vector index side by side, keeping both in sync as documents update, and then writing and tuning a fusion step that decides how to merge 2 different ranking systems into one ordered list. That's more infrastructure, more failure points, and a fusion weight that needs actual tuning against your own queries, not a default you copy from a blog post. Chunk overlap has a quieter cost, but it's real. If you're sliding your window forward with 100 tokens of overlap on 300 token chunks, you're storing a meaningful fraction of your corpus twice. Index size grows, embedding cost at ingestion time grows, and storage grows right along with it. For a small corpus, that's nothing. For a corpus in the tens of millions of chunks, that overlap is a line item. And query rewriting adds a dependency most teams don't think about until it breaks. Before retrieval even starts, you're now making an extra call to a language model to decompose the question, which means added latency, added cost per query, and a new place for things to go wrong, because that rewriting step can itself misread the user's intent and split the question incorrectly before retrieval ever gets a chance. None of this means the fixes are wrong. It means they're targeted tools with a real price, and the right move isn't to apply all 4 everywhere. It's to diagnose which of the 4 mechanisms is actually failing in your system, and pay only for the fix that matches the failure. Put those 4 fixes into an actual production system, and they don't run as separate experiments, they run as one pipeline, fused together at query time. A real retrieval stack doesn't choose between BM25 and vector search. It runs both on every query, gets 2 ranked lists back, and combines the scores before anything gets re-ranked, usually with something like reciprocal rank fusion, so a chunk that scores well on either signal has a real chance of surfacing, instead of one method silently overriding the other by default. Metadata gets applied at that same stage, not baked into the vector. Timestamp, document version, source authority, none of that is something an embedding can represent on its own, so it's enforced as an actual filter or boost at retrieval time. Query for the current config and the system can exclude anything flagged deprecated before similarity even gets computed, instead of hoping cosine distance happens to rank the current version higher. Re-ranking comes after that, and only on a bounded slice. You don't run a cross-encoder over a corpus of 1,000,000 chunks. You run the cheap hybrid pass first, take the top 50 candidates, and only those 50 get the expensive joint scoring. That's what keeps latency and cost predictable, regardless of how large the underlying index grows. And critically, teams that run this well monitor retrieval and generation as 2 separate systems with 2 separate metrics. Recall and precision get measured on the retrieved chunks themselves. Did the right chunk make the top K, independent of whether the final answer sounded fluent? Answer correctness gets measured separately, downstream. Those 2 numbers can move in opposite directions, and when they do, that gap is the diagnosis. If retrieval recall is fine but answers are still wrong, the problem is generation. If recall is bad, no amount of prompt tuning downstream will fix it, because the model was never shown the fact to begin with. That separation is the whole point. Every retrieval failure this pipeline produces is mechanical, traceable to chunking, embedding, query representation, or missing metadata, and every one of those has a specific measurable fix at the retrieval stage. That separation is what tells you which kind of problem you are looking at. A retrieval bug you can fix mechanically, or a generation problem that needs a different tool entirely. What it stops you doing is blaming the model for not knowing something it was never given.